Okay, so second chart is the one of the tool which is necessary to assist the engineers, the thermofluid engineers, the mechanical engineers to describe the situation or the analysis for a specific call it volume that of interest, and it relates to the humidity levels. And as described last week, there are a few definitions and call it terms or istilah that users of the theories need to be aware of. And the psychometric chart is just a tool that combine all the different definitions and parameters. So for example, here we have the specific humidity and the relative humidity. In assessment, sometimes you may have a question that asks you to define the term, what is defined as the specific humidity, relative humidity, and so on. And you need to outline also the related equation for those call it, definitions and terms. Okay, this is a psychometric chart, and then this is how you try to understand the location of the main parameters. The horizontal line is the dry bulb temperature, and then we have the curve representing the saturation line, and then we have the diagonal lines which represent the wet bulb temperature, the enthalpy, and also the specific volume, and we have the specific humidity as the vertical lines. Okay. So when we want to understand the concept of mixtures, because as mentioned last week, what we can control is the amount of water or moisture present in that specific volume of air, or you call it a surrounding. Okay, we allow your friend to enter. Okay, so you want to control the amount of water and moisture present. So because the air is there, unless you are dealing with a fully vacuum situation where there's nothing inside that particular volume. But when talking about conditioning the air, we want to control the presence of moistures and the presence of water vapor. So we take up the definition based on the mass balance analysis. So the mass of air is equivalent before and after that particular specific area of concern, and the same definition for the water. So let's say that you have a specific volume, then you know that the mass of air entering must be equal to the mass of air exiting from that particular area. So that's why in thermodynamics, the boundary condition is something crucial for analysis. So you really want to define which area that you are talking about. Okay, for example, you're talking about a room, so you're talking about call it a volume. So this is the volume of concern. So you know the amount of cool air that you want to supply in and the amount of heat that will exit from that particular volume. Okay. So we take on the energy balance analysis. So mass balance is the first approach, followed by the mass balance for water. So if you use these assumptions, you know that the air is there, and then what you do then, you can actually configure the amount of water that you want to supply into that particular volume. So so in here you need to separate into two different kind of perspective. The first one, we're talking about the physical present, the physicalities of the components. So we're talking about the molecule of air, we're talking about the presence of water. And in thermodynamics, we know that each of these will carry their own energy content. So this is the second part, is we look at the energy balance. So we analyze the amount of heat supply, the amount of work that we need to supply into the system. Okay, for example, you are providing the water into this cube of volume. So how much is the energy necessary to operate the water pump? Okay, how much is the energy required to operate the fan and so on? So that is the amount of work supply. Okay, and then you know that after the process is ongoing, will be the amount of heat rejected, and then if there is any work that can be produced, what will be the amount. So two balance, call it two balancing scenarios. The first one is the mass balance, that's followed by energy. Okay, mass balance refers to the physical aspect of the call it the event, and the second aspect is the energy that comes up or brings by or call it what are the energies that all those constituents will bring into the system. The work term usually consists of the fan work input, which is more relative to the other terms in the energy balance relation. Okay, so that's why from thermodynamics one, you always talking about the boundary condition. You're talking about, is it open system, is it closed system, and then we always talking about how much mass is entering and how much mass is actually exiting or escaping from that particular volume. In air conditioning process, so we're talking about four basic processes: simple heating, simple cooling. Sometimes in industrial applications, you want heating with humidifications, and sometimes for example, in the medical field or in the purpose related to food processing and so on, you want to provide cooling but without the presence of water vapor. So you want to provide cool volume of air, but with almost zero presence of water vapor. Okay, so again, it's talking about the specific volume of concern, okay, usually a simple room or anything equivalent. So we want to know what will be the quality of air. Are we going to talking about increase in temperature, or are we talking about the call it reduction of the temperature, or are we going to talking about the tempering with the relative humidity and also the specific humidity? Okay, so those element here represent how much water that you want to put in. Okay, so that's why you have devices to supply the water and devices that can assist the volume to take away, to remove the water vapor from this particular volume. So that is the basic operation of air conditioning units. Okay, and then you have the refrigerant, call it the refrigerant to initiate the heat transfer process. Okay, in a simple heating and cooling, okay, and then you refer to the psychometric chart. So for any residential heating, for example, if you have a heat pump or electric resistant heater, so how we increase the temperature is by we heat up the air by making sure that the air that is entering that particular volume will pass through a heating element, okay, or heating coil. So the same approach can be performed if we want to provide cooling by ensuring the incoming air will have a contact with a cooling medium or cooling system and so on. Okay, so heating and cooling on the second chart will appear as a horizontal line. Okay. Oops. One. Now you're front to enter. Okay. So heating and cooling appear as horizontal line since no moisture is added. So when there is no moisture, so there's no changes on the y-axis. It's only concerned on the horizontal journey, which is a reduction in the temperature. This is an example of a cooling process. The circle chart here refers to simple cooling, where the specific humidity remain constant. So here the specific humidities remain the same. Okay? But because you reduce the temperature of that particular volume of concern, okay, you once reduce the temperature, then the relative humidity will increase. Okay? If you remember the stochastic charts way of reading, this is the line of relative humidity. So once you move from right to left, so there is a changes in the relative humidity. So from the 30% it become 80% because the drop in the temperature, and sometimes with the constant specific humidity conditions. So this is a simple cooling event. So if you are talking about heating, then is the opposite directions. So you heat up, and then the relative humidity will reduce, will be reduced. So in this schematic process here, so you have the air coming from left to right, and the air mirror with the heating coils, and because the heating coil becomes a source of heat, that it transfer the heat from the heating coil to the air. So as a result, you're going to increase the temperature, and then the specific humidity will remain constant, but the relative humidity will drop. So during simple heating, specific humidity remains constant, but relative humidity will decrease. Why? Because the heat will temper or give some effect to the water content. Right. So in this analysis, everything is reduced to the enthalpy, because again, when we're talking about thermodynamics, uh, we want to locate and identify what are the enthalpies that involved in that particular process. Okay, so in this call it a simple representation of the psychometric chart. So we have, if you're being asked to sketch the system on a psychometric chart, then this is how you sketch the system. So you move from the right to the left to representing the drop in temperature, and also to indicate the increase of the relative humidity. Okay, because the x-axis is the relative humidity. Okay, and then the y-axis is the specific humidity. So this is simple heating and cooling. So cooling, you go to the left, and heating, you go to the right. Okay, so in relation to the psychometric chart. If you are facing with a situation of heating with humidifications, so you want to increase the temperature, but at the same time you want to increase the presence of water vapor. So you this is called heating with humidifications. So how you accomplish this demand is by passing the air first through a heating section, and then through a humidifying section. Okay, so the mass air balance remain the same, and then you have the water mass balance, and then you have the energy balance analysis. So schematically, this is what happens. So you have the heating section here, and then after you increase the temperature, T2 is bigger than T1. In here, you start to increase the water content inside the particular area. So you have the specific humidity increase. So if you look on the sketch here, it must go horizontally to the right, representing the heating. And because you're still having the heating process ongoing to affecting the incoming air, so it must go to the right. But since you have this device that add the amount of water inside the system, so the specific humidity will increase. So you need to sketch it upwards. Okay, so you have different value here. So this is the different in terms of specific humidity. Okay, so this is specific humidity at 3, specific humidity at 2 is here. So this is how you sketch. So you move from the left to the right and upwards to represent. Going outwards means that you are increasing the humidity inside the area. Going to the right means that you increase the temperature. So T3 is higher than T2, higher than T1. And then, of course, the specific humidity is higher than the initial conditions. Right. And also, there is changes on the relative humidity. Okay, cooling with dehumidifications. D means that we want to remove the humidity. So you have the word dehumid, we try to remove it. So the humidity of the air remains constant during a simple cooling process, but relative humidity increases. So relative humidity increases, so you move to the left. Okay. If the relative humidity reaches undesirable high level, it may be necessary to remove some moisture from the air. So, which means that you want to dehumidify, you want to remove the moisture's content. So this requires cooling the air below its dew point temperature. Okay. Why we want the dew point? Because we want to encourage the water vapor to liquefy. Okay. Vapor transform become liquid. For this to happen, we need to push the system to reach the dew point temperature. So we want the dew point temperature to be achieved, DDP as well, dew point temperature. Okay, so air, the temperature is really reduced, and then we have the cooling coil. So the cooling coil here encourage the attainment of the dew point temperature. So you have the condensations happening, and then you remove the condensate. So when you want to reach the dew point temperature, you push the system towards the boundary. So in here is where you can achieve the dew point temperature. So that's why we refer to the dry bulb temperature, and also we refer to the wet bulb temperature. So in any air conditioning system, then there are devices or components that can relay information related to the dry bulb and wet bulb conditions. Okay, and then so those are the process relating to the psychometric chart as a tool to assist the process. Next is the concept of evaporative cooling. So in a hot and dry climates, we can avoid the high cost of conventional cooling by using the evaporative cooler concept, which is also known as a swarm coolers. So the whole idea is that the moisture absorbed on the boundary here, and then the incoming hot air and dry air will help it to we'll call it vaporize. So the evaporation process will assist in the heat transfer process to take place. Okay. So as water evaporates, the latent heat of vaporization is absorbed from the water body and the surrounding air. So as a result, both the water and the air are cooled during the process. Usually, if you store your water inside a porous jug, so and then the incoming air, or create the moving air outside the container, will enable the evaporative cooling to happen. So for you to have the evaporative cooling to take place, you will need to encourage the liquid or the moistures to be absorbed at the boundary, and then will get in touch with the incoming air, because you know that when the air is moving, then it will help to call it increase the heat transfer process. So the evaporative cooling, okay, evaporative cooling is the concept that if you plot it on the psychometric charts, okay, so it's basically from point here to here, which relate to the wet bulb temperature reading, and also on the on the relative humidity reading. So here is the representing into the schematic. And when you do analysis relating to the evaporative cooling, so this is the assumption that you can take into account. First, you assume that the enthalpy will remain constant from stage 1 to stage 2. Okay, for those who are originating, or who are from a state of Perak, so you know that one of the, I call it, the product related to the traditional way of storing the water is what we call it the labu sayong. So if you have the opportunity to get a hold of this labu sayong, so you can see that the labu sayong is made from clay. Clay is the tanah liat, and labu sayong is as an example of the evaporative cooling process. So the water that is being stored inside the labu sayong, okay, it will be absorbed by the wall of the vase, and the incoming air will increase the heat transfer process. So if you have the opportunity to use one of these, and then you try to check the temperature inside the labu sayong, you know that the temperature inside this container is will always be much lower than the temperature from surrounding. Why? Because implement the concept of evaporative cooling. So why does evaporative cooling can achieve the cooling inside the container? Because based on the concept of the relative humidity. So the humidity that is absorbed here will increase the heat transfer, and then will ensure that the water inside the container will stay at much lower temperature in relation to the temperature of the surrounding. Another application of the evaporative cooling is by the innovators or inventors which adopt the concept of a frugal innovation. Okay, if you have the opportunity, you can also Google and search the concept of frugal innovation, and then you key in with the word of refrigerator. So frugal innovation means that you use the basic fundamental concept of any concept of scientific or technology or any basic concept, and then you try to implement without the use of complicated or high-end technologies. For example, this invention from the country of India. So they know they need to preserve the food, preserve the vegetables, but to have a working refrigerator is quite expensive because in remote areas in India, it's difficult for you to sustain the supply of electricity. So if the electricity is not stable, and the price of refrigerator is also very expensive in relation to the what call it, the remote areas populations, but they need to preserve the produce or the vegetables or the any food that they have. So one way that they can do this by adopting the evaporative cooling process. So this wall of this call it the refrigerator, which was made by using the material of using the clay material. Okay, so this is clay, and then the wall itself is behaving similar as the labu sayong concept. So the heat inside here will be transferred via the evaporative cooling process. So the temperature inside here will always be much lower than the temperature of the outside. Okay. So in doing this approach, the owner of the refrigerator, which is made from clay, which is much cheaper in terms of pricing, in contrast if you're using the commercial big refrigerator, they can still store the food safely and at the call it required temperature, and me still can enjoy the food after a few, I think not as long as a call it a proper refrigerator, but still much better in uh, if you compare against storage without a proper cooling or refrigeration. Okay, so this is a example of the aerobatic cooling, but just to call it to entice to invite your curiosity. Frugal is something which is of the interest, especially in these challenging years where you want to provide solution, but at a very low and economical cost. Okay, for example, being frugal means that instead of you open a shop to do business, so maybe you just open your shop online, and then you store everything at your house, and then you have all the couriers and the riders to deliver your products and so on. So that's how you make a frugal approach. Another way is that when you design and fabricate engineering solutions, you only stick to the functionality of the system, and you try to use the most basic and cheapest material available, but still maintain the functionalities of the system. Okay, so this is an example that representing the concept of evaporative cooling. Okay, in certain air conditioning applications, sometimes you need to mix the air with different humidity content. So you can use this approach. You can mix them, you branch off, or you can combine, so that you at the end you have working stream which is suitable for cooling your area of concern. Okay, next is the cooling tower process. Why we have the cooling tower? Because the purpose of cooling tower is that we want to cool down the steam, okay, escaping or after the turbine expansion process, and then we want to recollect, or we want to collect the cool steam so that it becomes liquefied into water, so so that we can put it back into the steam power plant. Okay. So the steam that escape from the turbine system, you want to increase the condensation behavior. Okay, so you use the cooling tower approach. Okay. So by doing this, the hot steam coming in from this, or hot water is spray down. So due to the heat transfer process, the collected water will be accumulated at the bottom, and then you supply it back to the system. So the steam here will be transformed back into the water. Okay, so you need to encourage the condensation process. Okay, so you have here the water, and this is the engineer. So you can imagine the size of the cooling tower. So power plants will often discharge their squirting water delivered into the ocean. Sometimes you need to discharge the we call it the water. Okay, but you cannot just dump the water into the ocean because there are some regulation, because you don't want to damage the ecosystem closer to the coastal line and so on. Okay, for example, if you search the by the Fukushima reactor in Japan. So when the cooling system experience a breakdown and malfunction, so the operator need to put in a external cooling process, and then they put in cooling water from the external source. But they cannot just dump the cooling water into the ocean, because you know that from the concept of heat engine, so you have the high temperature reservoir and the low temperature reservoir. So if you want to fulfill this concept, then the natural sources for the low temperature reservoir is the oceans, the sea, the river, and so on. But if you're dealing with a nuclear reactors system which is having a problem, you cannot just dump everything into the ocean, because it will damage the ecosystem of the oceans or the sea. Okay, so there is another challenge. So that's why you adopt the cooling tower to reduce the temperature to a safe working temperature. Okay. If the power plant is far from a water source, cooling tower is used to transfer the heat to the air, and then you can then collect back the water, so that you can circulate into the system. Okay. Cooling tower is I think almost every final exam will have this kind of questions, and it reflects back on the concept of the mass conservation of mass of the incoming air and the outgoing air, and then we have the mass balance for the water, and also the mass balance for the energy analysis. Okay, so this is at the campus in Utensham. There's also a cooling tower. Okay. Inside here, you have rows upon rows of elements similar like the radiators of your car. Okay, and then the hot water will be supplied to here, and then the incoming air will cool down the hot water, and then you reduce and you collect back here, and then you put back into the system. So this is the part 9. And then there's a cooling tower here. So for those who not really have the opportunity to visit the cooling tower, they may mistaken this plume of white, we call it white plume, as something may contain the smoke or so on, but it's actually this is a steam from the steam power plant. So you want to transform the steam into liquefied water at the bottom. So you do this by the intercooling concept, and then you can reroute the water again to the steam power plant. So you have this shape because you want to increase the heat transfer process. Okay, so this one is the natural draft cooling tower. So the warm water is spray outwards, and then hot air going upwards, and then you have the cool air coming at the bottom, and then you increase the process. So this is called the natural draft cooling tower. And if you don't have this permission to operate the, call it the cooling tower, so some power plant they put, instead of they um, let out the warm water inside the cooling tower, they spray out the water inside the big pond. Okay, so surface area, the larger surface area in contact with the incoming air will increase the heat transfer process, and then you can then collect it back into the system, because sometimes certain areas or countries, they are not allow any construction of towers like this, because they say that this will actually affect the landscape, affect the surrounding, and then create something which is not required by the local people or villages and so on. Okay, so if that is the case, then the power plant operator, they need to adopt the cooling, they need to adopt the cooling pond approach. Okay, instead of they have the natural draft tower, so they spray everything on top of a pond, and then they rely on the incoming air to cool down the steam. Okay, so those are what contains on the chapter relating to the mixtures, and the ability to read the circuit chart, and then to the ability to understand this process, giving example of the evaporative cooling, and then ability to do some calculations on the hot water or the hot steam. Okay, so this that's all about it for this chapter.